Everybody. So today's notes will be overwriting linear equations. A lot of this stuff, like I keep saying, is a review, so hopefully this will come easy to most of us. The essential question is, what are the different parts of a linear equation, and why do we represent linear equations in more than one form? So be sure to have these notes ready for Monday, September 14th, and then we will have a worksheet to do regarding this information. So if we look on to the first part of the presentation, an important part of a linear function is the rate of change. We've mentioned this term a few times in class. Identifying the rate of change can help us determine the behavior of a linear function, more so by determining whether it's positive or negative, and we can tell based on that what types of applications this linear function can help us with. A rate of change is a ratio that compares how much one quantity changes on average relative to the change in another quantity. So what we have seen before is this delta y over delta x, which just means the little delta or the triangle just means the change in y over the change in x. We've also seen it written this way as the difference between the two y values and then a difference between two x values. Basically what this is saying is that you're taking the change in whatever your dependent variable is. Oh, and you know what? This is a mistake. I'm sorry. Oh, no, that's not. Sorry. The dependent variable is always the y, because the y, or the f of x, that depends on my x value. So whatever my x value is, my y is the outcome, or the output of that, as we've discussed a couple times in class. So when we're talking about a rate of change, it is the change in the dependent variable divided by the change in the independent variable. So it's important that we become familiar with this terminology and that we are able to identify what the dependent and the independent variables are. We'll talk about it more as we get into word problems, but for now, just become familiar with this terminology. And then it's important to know that the rate of change is the slope. So if we are talking about that, probably be a good thing to highlight. Rate of change and slope, we'll talk about it in different areas. Those of you that are taking physics will see rate of change probably more than you will see the term slope, but they are exactly the same. So as long as you know that those are the same, that's really an important part of this. If we go on to our first example, we need to be able to determine what a rate of change for any given equation is. I picked this example in particular because there are a lot of people that are just so afraid of fractions, and I want to get rid of that stigma. So if we are going to solve this, what we need to do, or what I would recommend doing, is just getting rid of those fractions because apparently none of us seem to like them. So I would multiply both sides by the biggest denominator in there. We could multiply by the 2, but then we would still end up with a fraction over here. So always multiply by the bigger denominator. Probably a good rule to follow going forward. So if I multiply both sides by 4, 4 times 3, let's rewind. We can think of it as 4 over 1, same thing. When we multiply fractions, we multiply them straight across. So 4 times 3 gives me 12, 1 times 2 is 2, and then we've got my x. 4 times 5 is 20. 4 times 1 is 4. And then we can't forget that 15, so 15 times 4 is 60. We could put it over 1, not really necessary. So 12 divided by 2 leaves me with 6x. This leaves me with 5y, and then 60. So it looks a lot nicer this way. We can start to solve it easier. A lot of us are used to putting it into a y equals mx plus b format, so we can go ahead and do that. If I subtracted 6x from both sides, I would be left with negative 5y is equal to negative 6x plus 60, and then dividing by that negative 5. Remember that you have to divide both of these terms by that negative 5, so we're left with y equals 6/5 x minus 12. In this case, this format that we're used to seeing and that I'm happy that you guys are used to seeing, this is called slope-intercept form. And that is one of the forms of equations that we'll be talking about today. So slope-intercept form, the reason for that obviously is because you've got your slope that's easy to identify right here, or we can consider it the rate of change. And then we've also got the y-intercept here. And so this helps us with graphing a lot because we can start by graphing the y-intercept and then we can move up and down, left and right based on the slope or the rate of change. So a lot of us are really familiar with slope-intercept form, which is fantastic. The next example that we're going to get to is writing an equation when they only give you the slope and 1 point. So we've already been able to identify what a slope is, if our function is in standard form or in any other form. But going forward, we should be able to identify what a slope is or what an equation of it is by looking at the slope and a point. So if we do this, sometimes we can use a different form of an equation to help us write out an equation, if that makes any sense. So I'm not going to start with the slope-intercept form in this case. What I'm going to do is start with what's called a point-slope form. And so looking at this, point-slope form is written as y minus y1 equals m times x minus x1. It looks similar, but not quite. We've got two y values over here, you've got two x values over here, and sometimes this is an easier way or an easier form to put it in based on what you're trying to find. So in this case, if I substitute in my values, I can call this my x1 and this my y1. So if I substitute, I've got y minus 3 is equal to the 1/2 times x minus 2. And then I can start to simplify. So from here, I've got y minus 3 is equal to 1/2 x minus 1, because I distributed that. And then from here, I can just add 3 to both sides, and then I've already got an equation that is in slope-intercept form. So that's what's nice about using this point-slope form, is that once you simplify it and once you solve it, you end up with a function that's already in slope-intercept form, which makes it nice, again, to graph. So if you want to go ahead and label this or highlight it, this is called point-slope form. And this is another really useful way to write equations based on what it is that you're trying to solve or what is given to you. The next example is if we are writing an equation given 2 points. So this one is kind of a compound of different equations. We've talked about the slope formula before. So to remind us, the slope formula is m equals y2 minus y1 over x2 minus x1. So in this case, I'm going to start with that slope formula. If you're not familiar with this, then definitely label this in your notebook as a slope formula and highlight it. Make sure that you're familiar with it because you will see it a lot. So what I'm going to do here is label this x1, y1, x2, y2, and then just a matter of substituting in values. So I've got the positive 3 minus this 7 divided by negative 3 minus negative 2. So here, 3 minus 7 gives me a negative 4. This gives me a, let's see, 3 plus 2, so negative 1. So my slope ends up being 4 in this scenario. And then from there, I could go ahead and use the point slope form again, which I find to be pretty easy because, again, once we simplify it, it'll give us a nice equation in slope-intercept form. So using this, we said that the point slope form was y minus y1 equals m times x minus x1. So you can pick any one of these 2 points to be your y1 and your x1. So let's say I stick with these. I've got y minus 7 equals my slope, which over here I said was 4, times x minus this negative 2. So y minus 7 equals 4, and then this becomes a plus 2. So 4 times a positive 2 gives me a positive 8. And then adding 7 to both sides would leave me with y equals 4x plus 15, which is a really nice formula. We're able to find our y-intercept. If you were using, say you used the slope formula first, and then you decided, oh, well, I'm going to use that into my y-intercept form, you could have done that. So you could have plugged in your slope and then one of these points into y-intercept, and then solved for b, which really is your y-intercept. And then from there, you could have plugged it back into an equation like this. In my mind, that's a lot of plugging in and going back and forth. So this form of the equation is a lot easier to get a final answer or a final equation. So personally, I prefer this. It's really up to you. Whatever you're used to is also fine by me. Just another recommendation for you guys. And then the final thing we're going to do today is write an equation of a parallel or perpendicular line. So I'm going to show you both of them on this same slide. So be sure to differentiate both of them on your notes. So we're going to write an equation that passes through this point, and let me see, let me get an equation for us. We're going to use y equals -3/2 x plus 7. So first I'm going to start by writing an equation that is parallel to this and passes through the point 5, -6. And then over to the side, we're going to do an example where it is actually perpendicular and passes through that point 5, -6. So two different scenarios, two completely different equations, and we're going to show both different ways here. So if I look at this, I'm just going to separate these two with a line so we know the difference. Parallel, we know, means the same exact slope. So if I'm trying to solve something that's parallel, I'm going to use this exact same slope in my equation. So I'm going to start by saying that y equals -3/2 x plus b. So if I'm finding a new equation, my y-intercept is going to be what is a little bit different about this. So in this, I can go ahead and substitute my x and y values. So I know that's my x, that's my y. So I've got -6 equals -3/2 times 5 plus b. So -6 is equal to, and we can put this over 1 if we want to, so -15/2 plus b. But now I've got a fraction that I need to find a common denominator for. So I can write this as -12/2 because we know that is equivalent to a 6. And then that will help me when I'm adding 15/2 to both sides. So add 15/2. So in this case, 15 minus 12 gives me a -3. So I've got -3/2 equals b. This was the scenario that I was telling you earlier where you end up having to substitute back into your y-intercept form. So if I take this equation again, I've got y equals the -3/2 x, and then I've got another -3/2 here. So that ends up being the equation of the line that is parallel but passes through a certain point. I'm going to show you the other way to do it by using the point slope form rather than slope intercept form. So for perpendicular, I'm going to go ahead and start by writing the other form. So y minus y1 equals m times, sorry, that's an ugly m times x minus x1. So in this case, for a perpendicular line, we know that the slope should be the opposite reciprocal of whatever is given to us. So in this case, opposite meaning that I'm flipping it, or I'm sorry, opposite meaning that I'm changing the sign. So instead of negative, it's going to be positive. Reciprocal is when we flip the numerator and the denominator. So over here, it's going to be a positive 2/3 rather than a -3/2. So once I know that information, I can go ahead and plug into my equation. Again, we already labeled x and y, or x1 and y1. So I'm going to start by saying y minus the -6 is equal to 2/3 times x minus my 5. So I've got y plus 6 equals 2/3 x. Sorry, let me rewind. Let me just go ahead and distribute while I'm here. So 2/3 x minus, and then again, if we put this over 1, we would have 10/3 here. And then I need to find a common denominator because this is not in terms of thirds. So I'm going to rewrite it here. To convert it to thirds, we multiply by 3/3. So 6 times 3 is 18. 3 times 1 is 3. So now we've got this equation. And so I'm going to subtract 18/3 from both sides of my equation. So I've got y is equal to, that cancels out, 2/3 x, and then negative 10 minus 18 leaves me with a negative 28/3. And as far as I know, you cannot simplify that anymore, so that's what we end up with for the two functions. Keep in mind that you have to take the opposite reciprocal. Sometimes I have people flipping it, but they're not changing the sign, or they're changing the sign and not flipping it. So for perpendicular, be sure that you are doing that. Going forward, we're going to start talking about graphing. We probably will not spend too much time on graphing because I expect that you guys know that, and it seems from what I can gather that you guys do know that. So we'll graph a little bit, but I'm guessing that the next thing we'll talk about is how to write equations or how to write functions based on word problems. So that'll be our next focus going forward. I decided that I'm only uploading one video this weekend, so do not worry about watching another video. I'm anticipating giving a lecture on Tuesday, and then we can work on a worksheet starting on Tuesday and then going into Wednesday. So only worry about this video for this weekend. I will check these notes on Monday, September the 14th. So I will see you guys then. I hope you have a great weekend.